Welcome everyone to the final section in chapter number 3. This is section number 9, Antiderivatives. So we've been taking a lot of derivatives. What is an antiderivative? Well, in this video we're going to do the definition and intro. We're going to get a little experience computing these general antiderivatives. So let's get to it. Alright, first of all, the definition. A function capital F is called an antiderivative of the little f on an interval I if, when you take the derivative of capital F, the antiderivative, it gets you back to where you started, this little f, right? And this should be true for all x and I. Let's go ahead and play this game, right? And this will make more sense. So find an antiderivative for f of x equals 2x plus 3. So I'd like to find an antiderivative. Okay, so I'm going to do capital F, and I would like something so that when I take the derivative of it, I get back to little f, right? So staring at this for a little bit, let's go ahead and try something like an x squared, right? Because if I was to take the derivative of x squared, so I would get 2x, and that gives me this first piece. Okay, well, where does this 3 come from? What can I take the derivative of, and I would get 3? So let's go ahead and try. I think you would get 3x, right? So if I was to take the derivative of this, I would go ahead and get 3. Remember, we have nice addition and subtraction rules for derivatives. So this right here is an antiderivative, right? When I take the derivative of this, I get little f, this 2x plus 3. So you can see it's kind of like a guess and check sort of deal. Now, the claim is antiderivatives, right, are not unique. And by the way, before I go really any further, right, if you're looking at this and you say, this seems familiar, I think we've done something like this before, we have. And it was back in section number 2 here in chapter 3. Part of the mean value theorem, right, we did a strange consequence and we tried to find, right, we specified a derivative and we tried to find a function that had that derivative. So we're actually playing the same sort of game here. Now it has a more technical term, right, antiderivatives, but it's the same game. So again, find another antiderivative of 2x plus 3. All right, well, we already found one here, and we want to know how can we find a different one, right? Another one here. Well, the claim is, let's go ahead and start with f of x is equal to x squared plus 3x. But then if you were to add any constant to this, right? If I was to add plus 1, or if I was to add plus 5, or whatever your favorite number is here, you can even do crazy things like plus pi or minus 100 or something like this. Whatever you add to this here, well, when you take the derivative, let's go ahead, think about what the derivative would be, 2x plus 3, and then this would be, the derivative of 5 is 0, right? So whenever you add a constant here, right, you still get the same derivative, right? So this will also be an antiderivative of f of x. Okay, so there are infinitely many antiderivatives, right? Just plus any constant here. So we actually have a slick way of looking at this with this nice theorem right here, which says if capital F is an antiderivative, so if you found one of these things, right, it's an antiderivative of some little f on an interval I, then the most general antiderivative of f on I is capital F of x plus any old constant. So this is going to be called, again, the general antiderivative here. So plus any constant, right? Any constant will do, whether it's plus 0 like we had originally, right? Technically there's a plus 0 up here, or plus 5, or plus 100, plus pi, whatever you want, plus any constant, right? This is going to be the general antiderivative. Okay, let's go ahead and try a few problems. Find the most general antiderivative of the function below. So please pause the video, try to get as far as you can through these things, right? Look at both A and B. Try to do both of these, and then unpause the video, and we'll go through it step by step. All right, welcome back. Let me go ahead and find a capital F of x. So I need something that when I take the derivative of it, I get cosine, something when I take the derivative of it, I get cosine. So I think sine is going to be a good bet. Right? So let's go ahead and double check here. When I take the derivative of it, do I get cosine? Yes. So this right here, this is my just little way of showing that I'm checking my work, right? So that's what these arrows and all this green text is. Okay, something that when I take the derivative of it, I get 1 over x squared. Okay, so this is a little bit more difficult. Let me first of all go ahead and rewrite this really quick. I'm going to do this as x to the negative second power. So I need something that when I take the derivative of it, I get x to the negative second power. So thinking about how the power rule works, I would kind of maybe first propose x to the negative first power, right? Because then when I take the derivative of it, I'll have to reduce my power by 1, and I'll get x to the negative second power, right? But that negative 1 comes down. So this isn't exactly what I want, right? I want plus x to the negative second power. I have minus x to the negative second power. So somehow I need to alter this, right? This is a good first guess, but I need to alter this to try to get rid of this negative sign. So what if instead of adding x to the negative first power, what if I was to go ahead and subtract x to the negative first power, right? This is my good second guess. Okay, so if I subtract, then when that negative 1 comes down, minus a negative, this would become plus x to the negative second power. And now this is what I want, right? I'd like it so when I take the derivative of it, I get cosine of x plus x to the negative second power. So the plus here is the big thing. Okay, so this is how we can do a little bit of guessing and checking to try to solve these problems. All right, one more. General antiderivative. Oh, I forgot. This is good that I forgot. Maybe you guys did too. Most general antiderivative, we have a plus c. There we go. So this right here is our final answer. This is the most general antiderivative. Otherwise, it would have just been an antiderivative, right? But we could add anything. We could do plus 5, plus 100, right? So if we want the most general antiderivative, we do plus c. Excellent. Let's do one more here. Again, if you haven't tried this one, please pause the video, try it, and now I'll show you the answer. Okay, the way that we do this is that, well, we don't know how to kind of go backwards with antiderivatives with a product rule, right? So this has a product rule here, and we haven't really learned a way to do this backwards with a product rule. So let's go ahead and maybe distribute this. So again, I'm going to go ahead and rewrite first. I'm going to do 6 root x plus 7x root x. So basically, I just distributed this root x to each piece. And in fact, let's go ahead and rewrite this a little bit, right? X root x. Well, this is the same thing as x times x to the 1/2 power. And x is the same thing as x to the first power. So when you have these like bases, x to the first power and x to the 1/2 power, right? They're both base x, right? Those exponents, they add together. So this would be x to the 1.5 power. Or a better way to write that is just x to the 3/2 power. Okay, so this is how I would rewrite it. In fact, even really getting ready for, trying to figure out what the derivative is, instead of root x, let's go ahead and write this as x to the 1/2 power right here. Okay, so now I'm looking at this, and they really look like power rule things. Okay, so let's go ahead, and again, we're trying to guess what is the most general antiderivative. So if I was guessing here, I would say, well, in order to get an x to the 1/2 power, I want to start off with x to the 3/2 power, right? Because when I take the derivative of this, I'm going to have to reduce my power by 1, right? The 3/2 would come down, and then I would get x to the 1/2 power. And I like that x to the 1/2 power, right? I want that. But, okay, I need to get a 6. Well, when that 3/2 comes down, even if I had a 6 right here, right? And so that 6 would kind of follow along. This would give me 9, right? 3 times 3 would be 9. So somehow I need to get 6. So this is where, again, you need to be a little bit clever here. So because this 3/2 comes down, I'm thinking, okay, well, what if I put a 2/3 up here? A 2/3. So that way it would cancel with this 3/2 when it comes down, right? So let's go ahead and check. So again, when you take the derivative of this, the 6 is along for the ride, the 2/3 is along for the ride, and when you take the derivative of x to the 3/2, the 3/2 comes down and you reduce your power by 1. So now the 3's and the 2's, they perfectly cancel out, and I do get 6x to the 1/2 power, and that's what I wanted. All right, so again, if I want to get 7x to the 3/2 power after I take the derivative, I'm going to be thinking maybe, first of all, what about 7x to the 5/2 power? Again, I know that when I take the derivative of this, I'm going to have x to the 3/2 power because I reduce my power by 1, but then that 5/2 has to come down. That's the power rule. Again, the 7, that's a constant multiple. It's just kind of along for the ride. Well, this isn't exactly what I wanted, right? I would like to just have 7. So just like before, I multiplied by 2/3, which was the reciprocal of 3/2. Let's try seeing what happens if I multiply by 2/5, right? So if I multiply by 2/5 here, now when I take the derivative, the 7's along for the ride, the 2/5 is along for the ride, and when I take the derivative of x to the 5/2, the 5/2 comes down, and I reduce my power by 1. So I have x to the 3/2. And so you can see, again, these perfectly cancel out, and I get 7x to the 3/2. And that's what I want. So this looks good. This seems to be working. So let's go ahead and clean this up. Now, technically, again, let me write this so I don't forget it. There's a plus c, right? All right, so if I wanted to clean this up, right, the 6 and division by 3 kind of cancel a little bit. So I think I'm going to get 4x to the 3/2 here. And then plus 14/5 x to the 5/2. And if you're at all paranoid, right, you go ahead and you take the derivative of this one more time and verify that when you take the derivative of this, you get back to this little f of x, back to where you kind of started here. So this right here is the most general antiderivative. All right, that's it for this video. We have some more stuff coming up with these initial value problems. We'll do a few applications, but that's in the next video. I'll see you guys then.